Okay, now we're going to look at magnification for a spherical lens where the image is formed inside the lens, not outside the lens. So it's a similar picture to what we've looked at before. Again, the index of refraction increases. We usually go from air into something else. So we have the image. Now we have an actual image which has the height y. There are two rays that can go to this image. One goes straight through the center line. That's because this ray is perpendicular to the surface, and therefore there is no refraction. So rays that go straight in do not refract. It goes through the center and comes out here. The second ray we look at is one that goes through the center here, and we have an angle theta sub A, which is going to be related to the height of the image y and the distance from the image to the lens. So these are two sides of a right triangle. The right triangle being right there. Okay, then you have another case where you have another right triangle, which is this one. And you have the length would be S prime, the adjacent side, and the opposite side would be Y prime. And the angle is theta sub B. So what we can do is we have two things we can say. We can say the tangent of theta sub A, which is the angle of incidence, is equal to the length of the opposite side divided by the length of the adjacent side. Likewise, theta sub B is going to be equal to the tangent of theta sub B is going to be Y prime divided by S prime. We can also look at the relationship between, and let me use n sub A instead of n1, as I did last time. So n sub A times the sine of theta sub A is equal to n sub B times the sine of theta sub B. Now for small angles, not only is the sine of theta equal to theta, the tangent of theta is equal to theta, but we can also say that the sine of theta is equal to the tangent of theta. So Snell's law can become n sub A tangent of theta sub A, and that's equal to n sub B times the tangent of theta sub B. But I have the tangents up here, so I have n sub A times y over s is equal to n sub B times y prime over s prime. And there is a negative sign involved here. Why is that? Oh, it's because up here this angle is negative. Right, because this angle's down this direction. Okay, so if y prime is negative, then you'll end up with negative times negative is positive, and that works out. Okay, so you got a negative sign in front here, you got a negative, well, not there, negative sign when we do that, because we're going to substitute that into there. Okay, so the magnification is defined as the height of the image divided by the height of the object. So we can rearrange this. So then y prime over y is going to be equal to y prime over y. So we're going to have n sub A s prime over m sub B times, is that right? N sub A s prime, and we get a negative sign, and we've got that. So that's the result. And the our book, again using different terminology, it's the same kind of deal. They're saying magnification, capital M, is equal to negative n1 q over n2 p. This is the image, the distance to the object. This is the distance to the image. These are both positive quantities. So what this means is that if N1 is greater than or less than N2, which is the case if you're going from air to glass or water or something like that, and a negative sign means it's inverted. So you can say negative sign in the magnification equation indicates inverted image. So remember, the two kinds are upright and inverted. And the magnification is going to be typically be smaller. If you go back to the drawing here, you can see that the image is smaller than the object. Now, one thing, where does this actually happen? Well, in what cases do you form an image inside a spherical glass thingy-diggy? And the question would be, I don't know. But if you have a flat surface, that's seen more often, and we'll look at that next. So if you're looking at a flat surface like in water, in a lake or in a pool, then you do see that happening more often.